Good morning, everyone. Welcome to Test Prep Time Live. My name is Oliver Luisi. I'm the Director of Tutoring at Method Test Prep. I work with a lot of students all year long, and I'm happy to join you here this morning. As you may have seen, we've been doing a Test Prep Time Live every morning around 11 a.m., 15 minutes of quick strategies, concepts, key insights to help you on the SAT and the ACT. You can always revisit our page later on. These posted videos will stay live, will stay up after the live class, and you can review these at a future date or go back and check out some of the videos that you may have missed over the last few weeks. We'll keep doing this every day, weekday, Monday through Friday at 11 a.m. And today I wanted to talk specifically about circles. And I wanted to look at a specific idea within circles, which is primarily the idea of arcs. This is a very common concept that comes up on the SAT and the ACT. And I want to make sure you can see the key insights, the key ideas that come up with these questions time and time again, so you can start to recognize the same patterns that I would see, and it allows me to do these questions much more easily. Okay, there will be a couple of key or critical concepts we need before we even look at arc questions. We need to understand some basics about circles, including their circumference formula, which is pi 2r or 2r pi or pi d, r being the radius, d being diameter, depends on what they give you in the problem. Area, of course, looks similar, but a little different. Area here is pi r squared. And if you remember, area is usually in some kind of square footage, so that makes a little more sense why we have the squared radius there. Now, the last thing I've got up here on the screen is an arc formula, and there are a couple different ways to potentially approach arc questions. I found that using this proportion helps me solve 99% of every arc question I come across. And we're going to look at exactly what that means in a moment. Okay. When we talk about circles and arc questions specifically, just as a quick reminder of what we mean when we talk about arcs, okay? And I'll use the circle I have up here as an example before we jump into the actual question. An arc, just as a little refresher from geometry, an arc is a small piece or segment. You can see I'm tracing here arc AC. It's a small piece or segment of the entire circle, or more specifically, it's a little piece or segment of what is called the circumference of the circle, right? The perimeter. In most shapes we call it perimeter, but for a circle, the perimeter is called circumference. And this little arc AC is a little piece of the circumference. And that's exactly what arcs are. They're just a little part of the whole. So the arc is really just a little piece or fraction out of the whole circumference of the circle. Now that arc is actually created by the central angle coming out from the middle or center of the circle, which is cutting off the arc and creating the arc AC here. So this angle, whatever it might be, will always be exactly in the same proportion to the whole degrees in the circle as the arc is into the whole circumference, right? The arc is a little piece of the circumference in the same exact proportion that that interior angle that I've represented here by theta is out of all the angles, and we know all the angles in a circle are 360. A couple of key notes here. I've put this in degrees, 360, but on occasion you may see this part here being written in radians, where they use pi. You would just have to convert from radians to degrees, which is either pi over 180 or 180 over pi, depending on which direction you're moving, degrees to radians, radians to degrees. But most of the time we'll deal with degrees. One other note, here we're dealing with arc and circumference, which is really mostly the perimeter of the circle and dealing with the outside. A very similar question could ask you about the area instead of the circumference. So instead of arc and circumference, they might ask you about a sector, like a slice of this pizza out of the whole pizza. So that would be a sector or slice of the pie out of the whole area of the circle. The same proportion holds true. So whether you're doing an arc question or whether you're doing a sector out of area, the same proportion will hold true. It will be created by a central angle, and you need to find what proportion that is out of the whole angles, or 360 in a circle. Okay, as we look at this specific question to show you how this works, I need to note a few things as I start my problem. First, I want to pay attention to the picture they've given me. If they have not given me a picture, I should draw one. And that's a good rule of thumb across the math on the SAT and ACT on every geometry type problem. Whenever they mention a shape, if you don't see it, sketch one out. It doesn't have to be perfect, but it can at least orient you and give you some hint or idea of where the parts belong and what the relationships are. In this case, we already have the picture. We have a circle with a center O and a circumference of 36. What they ask for is the length of minor arc AC. Now, when they talk about length of an arc, if they give you units like centimeters or inches, then you'll measure it in that. Sometimes arcs can even be measured in degrees. It would just match whatever the degree of the central angle which creates it. But if they don't give any units, you're just going to answer in numbers. Sometimes might include pi. Why? Well, because we remember that circumference equals 2 pi r, or 2r pi. And so you might have a pi in your length. All right, we need the minor arc AC. So again, what we're going to do almost every time on these arc questions is we're going to fill in the pieces we have and then simply solve for the piece that's missing. Here we were given the circumference, 36. The arc, we don't know. This will be x. Then we have to set it up as a proportion where the central angle will be this angle. Now, in this particular picture, they've drawn a right angle. So this, I know now, must be 90 degrees. Now, if we didn't deduce that just from the symbol of the right triangle, the right angle at O, we could also maybe, there's not really enough information here without that symbol. If they didn't have the 90-degree symbol, I would have to figure out what portion of this circle is that angle. It looks like it's cut in exactly 4. So that would be another way to maybe deduce that it's 90. If you cut 360, the total angles, in 4, perfect 4 quarters, you'll get one of your angles as 90, specifically the one that creates the arc AC. So we do now know that central angle. I'm going to put in 90 here, and we know the total angles are 360. Now, anytime you have a proportion, 2 fractions with an equal sign in the middle, you can always cross multiply, and that would be fine here, especially if this was a calculator section question. You could just pull out your calculator and do that. But I always like to save time and really just to save effort and take a shortcut whenever I can that makes sense. In this case, I'm noticing the proportion. I can either reduce the 90 over 360 all the way down to its most basic form, but before I even do that, I notice a relationship here. My denominators are 36 and 360. What happened? Oh, I multiplied them by 10. Well, because it's a proportion, I need to do the same up here. That's also going to be multiplied by 10. So if I get 90 as the degrees, I must have multiplied what by 10? It must have been 9. So just as the angles are 90 out of 360 and creates an arc AC, we now know the length of that arc is 9 because the total circumference is 36. Correct answer is A. Okay, let's take a look at another example. Here, we have a similar setup, but now we're not dealing with circumference, we're dealing with area. So point C is the center of the circle above. What fraction of the area of the circle is the area of the shaded region? And that shaded region is just called a sector or a piece of pie. Okay, just as we would set up our arc questions, we're going to set up area the same way. The little piece or sector will be a fraction or part of the whole area in exactly the same proportion that the degree which creates it, the central angle which creates the sector or arc, is out of the total degrees 360. Okay, what is the sector? We don't know. That's X. What is the area? We actually don't know the area either here, but that's going to be okay because we actually just need to know the fraction, right? We don't know the actual area of the sector or the full area, but that's fine because it's just asking for the fraction. So really just the ratio of the little piece, the sector, to the big thing, the area. And so that will always be the same ratio proportion that the central angle is out of 360. And that's our fraction. But of course, I need to reduce this. And if I take out the zeros, I see that this is 10 over 36. I can reduce that even further, cut everything in half, 5 over 18. And although I don't have any choices here, this is a grid-in example from, for instance, the SAT. Here, I can pencil in my grid-in 5 over 18 as my fraction. Let's take a look at one or two more examples. Okay, now here's an arc question, but involves some extra pieces. And in fact, this is going to be a little bit of a puzzle. Now, the key to this question is going to be an important key for a lot of geometry problems in general, not just circles. And the key is going to be to find a hidden triangle. Now, triangles probably get a prominent place in geometry because we know so much about them, right? We know 1/2 the base times height is the area of a triangle. We know Pythagorean theorem. We could find the sides of a right triangle if we have the other two. We know SOHCAHTOA from trigonometry, sine, cosine, tangent. Those relationships are also really helpful. We also know a lot about special right triangles like 30-60-90 and 45-45-90. For this reason alone, if you can find a hidden triangle in a picture that you're otherwise stumped on, it's usually the key that unlocks the problem. Now, as we're going to see in this case, it's exactly what we need. Point P is the center of the circle above. What is the value of X? So they're asking for X, which is really this central angle here that's creating the arc BC. So they're asking for the angle measurement. But we're going to have to use the other information around it. We find out that these little acute angles are 20 degrees. And I can see that AB and AC are sort of chords, meaning they're lines that go from one end to the circle to the other without going through the center. If they went through the center, they'd be a diameter. So we have chords here. I can also see that PB and PC are radii of the circle. They're both radius. What can I do here? Well, I've had some clever students figure out a variety of different triangles that they can see inside this circle. You could draw a line from B down to C, and that would create an isosceles triangle because you have the two radii B in the sides. But that's not going to help me tremendously. Okay, if you spotted it, we could draw a line directly from A to P. That line would create two triangles. And again, by connecting A to P, I have written once again a radius of this circle. Just like PB and PC, AP is also a radius. Therefore, I now know that this side is congruent, equal to this side. Okay, that means I'm dealing with two isosceles triangles here. And if the two sides are equal, that means the two little angles are equal. So the 20 degrees here at B is also going to be matching to 20 degrees here. Same on the bottom triangle. The 20 degrees must match, because this is congruent as well, also being a radius, to the 20 degrees here. And now that I filled in the two acute angles of the triangle, I can use the rule that there's 180 degrees in every triangle. So I've got 20 and 20. What am I missing? 140. So this angle here, this big obtuse angle, is 140. And just because we know these triangles are identical, this is also 140. Okay, great. So now I have determined all of the angles going around the center except for this one portion, X, that I need to solve for. Well, how many angles in a circle? 360. I've got to subtract away the 140 angles I found. And what's left? $40 degrees. All right, 140 plus 140 is 280. Oh, should have used my calculator. Apologies. 360 minus 140 minus 140 equals 80. And so the remaining portion of this circle that we needed to find was this angle X, and this is going to be 80 degrees. Now, one way I could have double checked myself here if I wasn't sure, there is a more obscure rule in geometry that any angle which is created by hitting the edge of the circle, and we go out from A to B and A to C, the combination of these two 20 degrees into 40 will always be 1/2 of the central angle that's created by those same 2 points. So we see a central angle X here created by B and C. If we go to those same points B and C, but now instead of going to the center, we take a line out to the other edge of the circle at A, that little acute angle 40 will always be 1/2 of the central angle that corresponds to it, in this case 80. So that would be another rule you could turn to if you needed. And we find that the value of X is 80. Okay. I just want to mention we're also doing Test Prep Time Plus classes at 1 o'clock in the afternoon from Monday through Fridays. These are an extension of the type of strategies and ideas we're introducing here on Facebook. You can enroll right at that URL, jump on our website. You can sign up right now. Today, we're going to be covering diagram passages in reading and science. Tomorrow, we're going to be looking at misplaced modifiers on the English section. Every day, we're covering a different topic, plenty of examples. And you can chat in and ask questions, and we can look at specific problems together. We also do full-length classes, so if you're interested in learning more and pretty much all the concept strategies you need for the SAT or ACT, we have classes starting up every few weeks. Just jump online, and you can register right there, methodtestprep.com/classes. We also do a lot of private tutoring for the SAT, ACT online, as well as academic tutoring. So if you're doing schoolwork at home right now and need a little extra help, we do prep for those subjects as well as AP exams. And we also have our self-paced program, which is an excellent app that you can use on your own without a teacher or class that'll give you quizzes, videos, lessons, full-length exams, pretty much everything you need to know about the SAT or the ACT. It's 50% off right now if you purchase the subscription. Just put in the code FUTURE on our website and reach out if you have any questions. Again, we'll be here tomorrow at 11 for a little Facebook Live. And you can give us a call or visit our website for more information. I hope that was helpful today. The ARC questions come up quite consistently on both the SAT and the ACT, so just get used to them and be prepared for the type of, slight changes they might make, all centered around the same common theme of arc being a small fraction of the whole circumference or sector being a small fraction of the whole area. Both will be a proportion with the central angle that creates them. All right, have a good day, everyone.